We are going to continue doing problems of substitution. And so I have this problem here. We have the reagent is sodium cyanide, solvent is acetone. So we know that acetone is polar A product and with a good nucleophile that points to an SN2 reaction. Also, we see here that this is a secondary alkyl halide. So when you're predicting products, you take that into consideration, and we know the center is chiral because carbon here has 4 different substituents. Now, when predicting products, we know that this reaction happens with inversion configuration if it occurs at a chiral center. So predicting products, then, you would have an inversion at that center. Now, let's do one more problem. The structure will look similar. Let me see. Gonna change it a bit. So I'm gonna have a bromide here. Metal and ethyl. In here I have HBr. Well, that's aqueous. So now, in that condition, being polar product, and this substrate being tertiary, that points to an SN1 reaction, which means you're going to be forming a carbocation. What is a carbocation? So after that, the parts, you're going to form the following now, no longer drawing dashes and wedges because this is trigonal planar. Now what we need to consider is what's the nucleophile. So notice that we have HBr. Attacking with bromine is not likely because water is in much greater quantity being the solvent. So your nucleophile here is going to be water. And in addition to that, when you do the nucleophilic attack, you're going to create a chiral center. But since this is trigonal planar, the carbocation, the geometry, and you can have the attack from either side of the plane, you're going to create a racemic mix, a mix of enantiomers. So I'm going to draw one of them being, again, your nucleophile is going to be water attacking at that carbon. So I am going to be forming the following, and now I'm going to do that. You're going to create an alcohol, that plus the enantiomer, right? Because we're forming a racemic mix. So again, always the analysis then that you're going to be doing is reagent, and then we're going to be looking at the structure of the substrate. Now I'm going to give you another example in which we don't have an alkyl halide. So let's do, I'm going to change this because you can have substitution reactions with other substrates. Say that I'm going to start here with an alcohol. Because alcohols, we can have substitution reactions as well. But what happens in when we have substitution reaction with alcohols is that OH is a bad leaving group. So that's a secondary alcohol. And so depending on what we want to do, we will choose the reagent. Say that my target, let's see, I'm gonna now say that I want to substitute that, but I'm gonna do a wiggle line here. Let's say that I wanna make an alkyl halide from that. I don't know the configuration yet. That is a chiral center. But in principle, if this is secondary, if you want to do an SN2 reaction in this place, OH, you're gonna do that with, say, sodium bromide. Essentially, this is too bad of a leaving group. So you have 2 options. If you go in SN2 and the condition is basic or neutral, you want to make this a better leaving group. So here what you do first is react with tosyl chloride. When you react with tosyl chloride, and I'm gonna do the structure here. So paratoluene sulfonic acid in the chloride is this. So that's tosyl chloride. So essentially what's going to happen is the nucleophilic attack here and that the parts, well, not exactly in one step, but we can summarize. First, we will have this, and then you will have the departure of chlorine. So at the end of the day, what you're going to form is the following molecule. Notice that here I'm writing OTS. And so what we are doing is substituting this, the H by that group, which is now a very good leaving group. Another thing that I want you to notice is that since the reaction did not touch the chiral center, the configuration here stays the same. So we react, the reaction what? With the oxygen. Now I have a good leaving group. And now I can do the reaction. If I wanted to do this, I could, because now that is a good leaving group and I can make that. However, we need to be careful with the configuration. If you have that attack over here, that'll be an SN2 attack. If we do that, say that we have the MSO, polar A product, say that we do that. And if this is a condition for an SN2, now you're attacking at the chiral center. Therefore, you would have an inversion of configuration because, again, that center is chiral and the attack is from the backside. So if you did that, now this is going to be dashed line. So inversion of configuration at that chiral center. So that is, if you want to do reactions of substitution with alcohols under neutral and basic conditions, you want to transform the OH in a good leaving group, so you use tosyl chloride. And I'm going to give you yet another option that we have with that. Say that I now work with other conditions. This is secondary. So having a secondary alkyl halide give me the option to work under SN1 conditions or SN2 conditions. But again, question is that the problem is that we have is that this substrate has a very bad leaving group. So another way to make it a good leaving group is to work under acidic conditions. So now if I work with HBr, and that's aqueous, what I will do first is an acid-base reaction, which will now protonate the OH group. And in protonating the OH group, now we're making that a good leaving group. So because the secondary can go SN1 or SN2, here the condition is SN1. So I am going to form a carbocation that in this case is secondary, and then you can have the attack by bromide. Here, remember that here you have also a hydrogen, so when you put the bromide here in the geometry again, trigonal planar at the carbocation, and here you have metal, propyl, hydrogen. So when you put the bromide here, you're going to be making a chiral center. And because of this geometry, you're creating a racemic or racemate. A mix of enantiomers 50-50, in other words, because of the attack being possible from either side of the plane. So 50-50 mix of enantiomers is a racemic mix. And so that's the product that you're forming. I can draw just one of them. And that plus the enantiomer. So you would draw that on a wedge, for example. So that's it. That's again, substitution and elimination reaction. And we have considered possible reactions with alcohols under both, say, basic conditions and acidic conditions to make the OH a good leaving group. What do we need to do in those cases?